이번 섹션은 랜스, 스티븐 웬드께서 성공적인 가속 중성자 평가를 위한 로스 알라모스 사내 전문가의 가이드라인을 발표할 예정입니다. 박사님은 로스 알라모스 내셔널 라바토리의 랜스 물리학부 기술 프로젝트 관리자이시며 최근 반도체 전자장치의 방사 효과 및 중성자에 의한 고장의 반도체 장치 테스트용 시설 및 기술 개발에 깊은 관심을 가지고 있습니다. 그는 지상 중성자 테스트를 위한 랜스 시설을 개발 운영했으며 항공기 고도에서 열 중성자 및 기타 입자에 대한 탐지기를 개발하고 있습니다. 박사님은 뉴욕 시립대학 학사학위, 아이오와 대학 물리학 박사 학위를 받았으며 캐나다 맥메스터 대학, 미국 듀크 대학, 트라이앵글 대학 원자력 연구소 및 스웨덴 스베드버그 라바토리 연구소에서 근무했습니다.
Stephen Wend will present Los Alamos in-house experts guideline for successful accelerated neutron test. He is the technical project manager in the physics division at the Alamos Neutron Science Center, also known as LANCE, at the Los Alamos National Laboratory. Recently, his interests include radiation effects in semiconductor electronics and developing the facilities and techniques to test semiconductor devices for neutron-induced failures. He has developed and operated the LANCE facilities for terrestrial neutron testing and has been developing detectors for thermal neutron and other particles at aircraft altitudes. He received his BS degree from the City College of the City University of New York and a doctorate degree in physics from the University of Iowa. He has worked at McMaster University in Canada, Duke University, Triangle University's nuclear laboratory in USA, and the Svedberg Laboratory in Sweden. He is a fellow of the American Physical Society.
Let me first thank the organizers of this meeting for giving me the opportunity to present the LANCE facility and our capabilities in terms of testing semiconductor parts. This is something we've been doing for over 20 years, started in the early 90s with the Boeing Corporation, and this has grown to be a very well-used capability that we have at LANCE. So this is sort of a quick summary of what I'd like to talk about. I'll say a few words about the terrestrial particle flux that we're all subject to. What I'd like to do is talk to you then about the capability that we have at LANCE for neutron radiation effects testing, our facility, and this is for the terrestrial neutron spectrum. I'll spend some time talking about time of flight measurements, which is a rather unique feature of LANCE. I'll spend some time talking about how we measure the neutron flux, and then finish up with some recent measurements on power MOSFETs that we've made using this time of flight technique. So I'm sure I don't have to explain to the people at this meeting about single event radiation effects, single event effects. These are failures in semiconductor devices, upsets in semiconductor devices caused by radiation. Particles from the sun and from the galaxy impinge on the Earth's atmosphere. These particles, typically GeV protons, interact with the atmosphere, the oxygen and nitrogen, undergo a bunch of nuclear reactions, produce all sorts of things, and also produce neutrons. Neutrons, because they're uncharged, make it all the way through the magnetosphere, the magnetic fields of the Earth, and through the atmosphere. And what I've shown here is they can interact in airplanes, large data centers, cars, in fact, anything that has semiconductor devices in it. These neutrons then produce nuclear reactions in the semiconductor device, the silicon, and produce charged particles. Could be a recoiling silicon atom, could be an alpha particle or some other species of proton. These particles, these charged particles, traverse the material, depositing energy, producing charge, which causes semiconductor devices to upset. This is a picture of the radiation flux hitting the Earth, what I call the terrestrial radiation flux. On the left, I have the sea level particle flux. On the right, the particle flux at aircraft altitudes. And you see this top curve are for neutrons, and that's the greatest source of radiation at sea level. The green curve are electrons, which their direct ionization is generally thought not to produce enough charge to cause the device to fail. Neutrons interact with the silicon through nuclear reactions, produce charged particles, and they produce significant charge. And I'll show you more of that later. The red curve is protons. As you go to higher, and at the higher energies, protons become significant, but they're still, their total magnitude is considerably less than the neutrons. As you go to higher altitudes, the heavier ions, the alpha particles, carbon and oxygen increase. And eventually, when you get to space, those become the dominant radiation that semiconductors are exposed to. If you compare these two curves at sort of mid neutron energies, the difference between sea level and aircraft altitudes is about a factor of 300. So the incident flux is much greater at aircraft altitudes, which is one of the reasons the aircraft industry is so interested in this. These calculations were from a very nice spreadsheet program from the Japanese Atomic Energy Agency. So the number of failures is a combination, a convolution of a cross-section convoluted with a flux. The flux depends on the particle type, the altitude, latitude, solar activity, local geometry, basically the environment you're in. The cross-section depends on the internals of the device characteristics, how it's made, the particle energy, particle type. If you know these two quantities, you can calculate a failure function, a number of fails you get. But the problem is we don't know, it's very difficult or not easy or not reliable to calculate the cross-section. The flux, I think we have a pretty good idea of, but the cross-section is difficult. Because it's difficult, you have to do testing. You have to do testing because calculations are not reliable. And you have to do accelerated testing. And if you go through this little arithmetic, let's say you design or are building a computer system and you want it to fail only once a year from single event upsets, and you want that failure rate, you want to know that failure rate to 10%, you need 100 fails. Well, if the system really fails once a year and you get 100 fails, that'll take 100 years. And that's obviously not going to work. So you have to form accelerated testing. If you have an acceleration factor of say 5,000 or 36,000, you can get the answer in a week or a day. That's if you're testing the entire system, but that generally isn't good enough because you want to know the answer before you build an entire system. You want to just test the single chip. Well, let's say there are 300 chips in the system. So this acceleration rate is going to have to be a factor of 300 times more. So you need something like an acceleration factor of 10 to the seventh if you want to get your 10% number on the number of fails in a day. Well, fortunately, Los Alamos has a facility for doing this, and I'll talk about the Los Alamos facility. There are other facilities in the world. There's that do neutron testing. There's one in England at ISIS. There's one in Canada at Triumph. But I'm just going to talk about the Los Alamos facility. It's based on an 800 MeV proton LINAC. It's about 1 kilometer long, and it feeds several experimental areas simultaneously. So all these experimental areas run at the same time. We have a high energy neutron source where the beam is directed to that area. This is where we do our testing for semiconductor devices. We also have a proton source in the energy range from 200 to 800 MeV, which can be used. The Lujan Center is for low energy neutrons from subthermal up to maybe 100 kilovolts. A future proton source, this was the area where they did most of the nuclear physics experiments, and they delivered over 1 megawatt of beam to this area, but this area is not currently being used, but we're proposing it for a proton source. An ultra-cold neutron source for basic science research, proton radiography, and an isotope production facility that produces medical isotopes for medical diagnostics and therapeutics. So of course, the problem is it's very hard to make high energy neutrons because you can't accelerate them because they don't have any charge. So the way we produce neutrons at LANCE is by what we call spallation reactions. Spallation reactions take a high energy proton, slam it into a heavy nucleus. In our case, we use tungsten, and that produces our neutron spectrum. In the beginning, these high energy neutrons, by direct reactions, the high energy neutron transfers all its energy to 1 or 2 nucleons. So the highest energy neutrons are proton, and protons are kicked out. So the direct reaction of the high energy particles. Later, the proton shares its energy among several nucleons, so heavier particles are emitted. Things like alpha particles, deuterons, in addition to the neutrons and protons. At a later stage, the energy of the incident proton is pretty much shared between the entire nucleus, and particles just evaporate out. The total energy is conserved, equal to the incident energy, so you get lots of low energy particles. Eventually, there's not enough energy to knock off these particles, so the nucleus just decays by gamma rays. At 800 MeV, the energy of our proton beam, we produce about 18 neutrons for every proton. Okay, again, proton beam hits a tungsten target, produces lots of things. The charged particles are removed by magnets. They're swept down by magnets. The proton beam is pulsed, so time of flight techniques are possible. And this is an important feature of our facility. And the time structure consists of a large-scale time structure, 625 microsecond wide pulses, which repeat 120 times a second, 8.3 milliseconds between these macropulses. Within these macropulses or micropulses, these are very sharp pulses, nanosecond wide, typically separated by 1.8 microseconds. So we get about 34,000 of these pulses a second. These proton pulses strike our tungsten target, and a pulse produce a wide range of particles. If we stand back away from this target, a distance L, what we call a flight path length, then these particles sort themselves out by their energy. The fastest ones, it's like a race. The fastest ones get to the end first. So the gamma rays, which travel at the speed of light, they're the fastest particles. They stay together as a bunch because they all travel at the same speed. The next thing to come along are the high energy neutrons and eventually the low energy neutrons. So if you can measure the time of arrival of an event relative to when the pulse hit, if you can measure this time, you can calculate the speed of the particle because you know the distance. The speed is just this distance divided by this flight time. And if you know the speed, you can get its energy. So to give you an idea of what numbers are involved, if you have a flight path that's 20 meters long, which is kind of typical of what we have at LANS, a 1 MeV neutron takes 1.5 microseconds to get from the target to the detector. 100 MeV neutron takes 150 nanoseconds to arrive, and the gamma rays only take 67 nanoseconds. Okay, so it's important to be able to measure the neutron spectrum so we know what's hitting the parts. We use a fission ionization chamber. This is just a gas-filled chamber with a thin foil filled, covered with a fissionable deposit. In our case, we use uranium-238. So the neutron beam comes in to this chamber, fissions the U-238 into two heavy fragments. The two heavy fragments deposit energy in the gas, and we analyze that pulse for both the time of arrival, remember we need a timestamp, and the energy of the particle. The monitor is thin, so it doesn't perturb the incident neutron energy. And the pulses are sharp, so we get a good measure of the time of flight, which we can use for getting the neutron energy. So the number of neutrons per second per MeV that we record, that we calculate, depends on the number of events that are generated in this chamber, divided by the fission cross-section, divided by the thickness of the foil. We already know these numbers, so we can, and we measure this, so we can calculate the energy spectrum and the absolute number of neutrons that pass through the detector. Here's a little bit more detail on that detector. If we plot the energy deposited in the chamber versus the time of flight, we get a spectrum that looks like this. If we project the total energy deposited, we see two lumps here and here. This is the lump from the heavy fission products, which deposit a lot of energy. This little peak here are from alpha particles, which are produced at high energy due to neutron-induced alpha particle reactions. So here are the high energy neutrons. If you look here, there's a band of particles which all occur at the same time at all different energies, and those are the gamma rays. If we project these down to the time of flight spectrum, we see a small peak here, which corresponds to the gamma rays, then the high energy neutrons, and then eventually at later times, the low energy neutrons. This is what our facility looks like. A proton beam comes into the neutron production target. It is in a vacuum chamber, which is about 2 meters in diameter, and a massive shield about 8 meters thick of steel and concrete. And there are penetrations in this shield for the neutrons to come out. On each penetration, there's a shutter which can be opened and closed by experimenters independent of the others. So each experimental on each one of these 6 flight paths can control their neutron beam. But all these flight paths operate simultaneously. So we built the first electronic radiation facility called ICE-1, ICE standing for Radiation of Chips and Electronics, in about 2004. It was quickly filled with people using it. So about 8 years later, we opened up another flight path called ICE-2. Energy spectrum we get from our production target depends on the angle of the angle between the proton beam and the neutrons going out. So if you look at this plot here, the 15-degree spectrum is in red, which gives you the highest energy neutrons. This is the most forward flight path. On the other hand, the 90-degree spectrum at 90 degrees to the target is this black one, which gives us the lowest energy, or gives you fewer high energy neutrons. So what we did was we compared the terrestrial neutron spectrum that was measured by Paul Goldhagen with these different angles, and we decided that the best fit was at 30 degrees. And on the plot on the right here, you see the red spectrum is what we have at WNR, and the blue spectrum is the spectrum that was measured by, is the cosmic ray neutron spectrum that was measured by Goldhagen. Another thing that's very important is in doing these measurements is knowing or being sure that the beam is uniform. Many people put many devices at different, or the same devices at different locations within the beam spot. And if the beam isn't uniform, you will get wrong answers. So this is a picture. We put what we call an image plate. It comes from the medical profession, and get a picture of the beam spot. This is a line out through the center, and you see it's fairly uniform across the top of the beam spot. This is ahead of a device. This is behind the device. And in fact, you can see the image of the device on the film looking behind the device. One of the problems with this approach is that the film is sensitive to lots of things, and it might not be just high energy gamma rays. So it would be very useful to develop a device that would be sensitive just to high energy gamma rays to characterize the uniformity of the beam spot to just high energy gamma rays. Okay, maybe I won't spend too much time on this. This is for my friends in nuclear physics who want to know what particles are produced and what the energy spectrum of particles are produced when neutrons hit silicon. And you can see if a 30 MeV neutron hits silicon, it can make a maximum of a 6 MeV silicon recoil with a range of about 3.6 microns and energy loss of around 2,750 kilovolts per micrometer, which you can convert to a charge. If you have a higher energy neutron, you can give more energy. You kick the silicon harder, it goes further, and it has an energy loss. On the other hand, if you make an alpha particle, and this is an example of a 50 MeV neutron will make a 40 MeV alpha particle or a maximum energy of 40 MeV alpha particle. And you can see its range is considerably longer, but the amount of charge deposited is a lot less. So alpha particles go further, less charge, and it's not clear they have enough charge to cause the device to fail. And our theorists have calculated and experimentalists have measured these distributions. Okay, so I'd like to show you an example of what we've done with these measurements. The problem is, of course, a lot of people that come to our facility are companies and they do work in proprietary mode and we don't talk about it. This is a case where people in our laboratory actually measured something so we can use their data. This is an IGBT that we put in the beam, and we were interested in what happens in a radiation field to the IGBTs because they were being used to build a neutron source. So we put the part in the beam these were 3,300 volt IGBTs. Here's the rated voltage. We started out at 500 volts. We put it in the beam for an hour and it worked fine. We went to 1,000 volts, worked fine, didn't fail. We got up to around 1,500 volts, and at least in one case, it failed very rapidly. As we kept increasing the voltage, they all failed very rapidly. And the thing that I found interesting in this was that this threshold voltage was considerably lower, almost half the rated voltage. So the lesson I took from this was that if you wanted to run one of these IGBTs and not have them fail, basically you had to derate them almost by a factor of 2. And what we did, by the way, when we said they failed, they went bang, it sounded like a gunshot, and it was destroyed. So we lost the whole IGBT. More recently, we did some measurements on MOSFETs, and what we noticed was that if we put a current limiting resistor, this is a simple circuit of the MOSFET with a current limiting resistor, then when it failed, it didn't destroy itself. It just gave us a pulse through this blocking capacitor, which we were able to send to our data acquisition system and actually do a time of flight measurement. So we were able to record that it failed and that we knew what energy neutron caused that failure. So this is the results of that measurement. These were pretty fast measurements. We measured it, I think it was rated at 1,000 volts. So we did it at 1,000 volts. We derated it to 850 and even more to 750. And we actually measured the failure cross section. So the red curve here is at 1,000 volts, and you see the cross section is about a factor of 10 higher than the 850 volts, which it was derated to. And if we derated it to 750, it was again, the cross section was lower, almost a factor of 10, not quite. So if you derate it, the cross section would be less, it would last longer. And so that's one thing we noticed. And the interesting thing here is now we can actually use that formula that I showed you at the very beginning of my talk to convolute the energy dependent cross section with the energy dependent flux and actually calculate a the failure rate in a particular neutron flux. And we haven't done that yet. I'm planning to do that. It would be very interesting to compare that with the flux that we measured, the average over the entire spectrum. And knowing the energy dependence is important if you're going to try to understand what's going on, if you're trying to do shielding or anything. This extra information is, I think, very valuable. The other thing to notice is that there's an onset that is at around 10 MeV, where the cross section is very low for almost all voltages, and it sort of rises. In this case, it looks like it rises a little bit below 10 MeV, but sort of in the 10 MeV area, which is, I think, generally accepted. Okay, so look, let me quit and summarize that LANCE, I think, is an excellent place to test these semiconductor devices in a terrestrial neutron spectrum. We have a good match for the terrestrial neutron spectrum with an acceleration factor of around 10 to the 8th compared to sea level. Time of flight techniques allow us to first measure the neutron flux very precisely and directly. We've also been able to measure the energy dependent single event upset cross section with this broad spectrum beam for devices that produce a fast upset signature like power IGBTs. And we've shown we can do that. And in fact, we're also working on approaches that will allow us to measure the energy dependent cross section for any digital device like SRAMs and so on that don't have fast timing signals. So let me quit here, and hopefully there's some time for questions.